and we will go ahead and get started. My name is Charles Lively, and I'm a science engagement engineer here at NURSE, and I'm also joined with my counterpart and colleague, Dr. Lippy Gupta, as well. For those of you that do not know us, we're a part of the user engagement group, and we'll get into what we do here at NURSE, and Lippy and I will share a little bit of our backgrounds. Just a little bit of overview of the agenda. We'll start with just a few housekeeping things and introductions. And part one of this bird's eye view in CUDA C++ is going to give you an introduction to working with CUDA C and learning about threads in CUDA. Part two will get into more detailed or more advanced topics related to like thread CUDA threads, as well as more optimization strategies in CUDA as well. So look at this part one as more of an introduction and setting the scope of everything. So again, here at NURSE, we're part of the user engagement group, and just like the name alludes, it's our goal and our mission to engage actively with our users and provide a welcoming and helpful environment for all of our nurse users to achieve their scientific goals using our resources available. And so I'm Charles Lively. I've been with Nurse for about 2.5 years now, and previously used Nurse when I was a graduate student at Texas A&M. It was Seaborg. It was Nurse N3, I believe. So my background and my PhD is in computer engineering, mainly focusing on performance modeling and optimization of scientific applications. So I always have looked at it like I get to learn a little bit about different scientific areas because I might work with a physicist or someone doing climate simulations or, someone doing, dark energy studies. So I get to learn a little bit about everything. And I'm also again joined by Lippy Gupta. And Lippy, did you want to share a little bit of your background?
Sure. So my background, I'm actually a physicist. So I have my PhD in physics and particularly in accelerator physics. But I was using NERSC's, not the current system, but the previous system, Corey, during my graduate work. Um, and in the process, just became really interested in high performance computing and how we can sort of help other scientists like myself at the time make better use of the systems. And that's kind of how I ended up here at NERSC as a staff member in user engagement. Both Charles and I are scientists turned, HPC. I mean, Charles did his PhD in computer science, but we have an academic background, and so it kind of helps us, communicate with the all of you, the scientists that we work with, and understand kind of how we can help, what kinds of things are you looking for, and then we just facilitate those kinds of either events or programs. So yeah, thanks all for being here. I'm not a CUDA expert. I'm learning along with Charles. I know Charles is always learning, but I'm learning along with him. So I'm gonna keep an eye on the Q&A doc today. But I may not be answering them, but I'll try to make sure that, if your question isn't answered immediately, it's because, when there's a break, I'll kind of alert Charles and then he can address it when he has a moment to do so. All right.
Awesome, awesome. Thank you, Lippy. Glad to have you here helping out. And so again, this is our team, our group that we are a part of with our fearless leader, Dr. Rebecca Hartman Baker. We have a number of different people of different backgrounds on our team. As Lippy stated, she's a physicist. We have, others that are into UX and UI experience and design, like Margie and Annette. And we have nuclear engineers like Kelly as well. And we have other people with physics and geophysical backgrounds like Helen, who's our lead technical trainer. So everything we do here is to help try to engage users to be more productive. And so if you are not a part of the Nurse Slack, we want you to make sure you join. That's an easy, quick way to learn about some of the latest trainings and events that are going on, as well as get help from other users. We have over 10,000 users here at Nurse, and many are working collaboratively on different scientific projects. So if you're ever stumped or having a problem, you can always submit a ticket as well as reach out to other users in the Nurse Slack. And so all of our training events and training videos are recorded, and then those recordings are posted on our Nurse YouTube. So please join. Again, these slides are also in the Q&A doc as well, so you can get a PDF access to that too, as well as access any of our previous training events and our training archives as well. Okay, and so the Q&A doc that we will be using is listed here as well. And again, at the end of this call, please make sure you complete our survey to help us know how we're doing and what you found helpful or what things you would like for us to maybe add for future training topics. Again, slides and videos are all available. We encourage all of our users to also join our Perlmutter office hours that we're having throughout the summer. It's an easy, quick way for you to drop in and get assistance and help for any issues that you're having on Perlmutter. All right. So a little bit of housekeeping and things to make sure you consider is that the examples that we'll go over briefly today are available in GitHub for you to use and to try out, and as well as you can also just execute those as well as make use of the training account that the training reservation and training project account that you have access to throughout part one and part two of this series. So if you're an existing nurse user, then you should be added to TRN 017. If you're not a nurse user and you did not apply for a training account, please make sure you do that today for part two. Unfortunately, if you don't have a nurse account and you did not apply, we will not be able to approve you during this session, but for it'll be valid for part two as well at the end of August. And so our reservation just for during this training time is NUG underscore CUDA underscore C. You'll use account TRN 017 for any job submissions that you use. Now, remember the reservation is only during this time frame. After that, you can remove the reservation flag and just use the training account allocation. All right, and so we will get started with diving into things. So one thing that a lot of this first part of part one deals with is focusing more on understanding computing from a heterogeneity from a standpoint where we have different computing units that we're able to make use of to achieve our goals. So it's about leveraging some of the different devices that are now available on our hardware to, maybe exploit latency and get high throughput and performance through those devices as well. So a lot of working with CUDA and working with GPUs is also realizing and understanding what in your science needs to be advanced. And so heterogeneity can and computing can come in various facets. So it can include having various multiple cores that you're able to make use of. latency cores to exploit that, as well as throughput cores for processing of more data. And then you also have hardware components that you're able to make use of. And so you might have, digital signal processing cores, other configurable logic cores that you can make use of as well to get a good exploitation of all of the resources that are available. And that includes being able to leverage um, different memory hierarchies and memory architectures that are available off chip as well as on chip, or as well as within the node as well as off the node too. So computing is definitely taking a more hierarchical progression, and that's going to allow for us to make use of different heterogeneity, heterogeneic structures, computing structures that we can use as well. And so that also means being able to integrate cloud services. And so one thing that we also have to take into consideration is, again, understanding the focus and how CPUs and GPUs are serve very different purposes, and they're really designed very differently. With CPUs, they're more geared towards latency-oriented cores, and you have different components that you can exploit, such as more a larger cache to make use of for on-core memory as well. And then you have different registers and other units and control devices that you can make use of. GPUs are more architected to be more for throughput, for making use of quick calculations that can be done in parallel. If calculations that don't require a large amount of cache or local memory for quick access. So you can easily make use of that and use multiple GPU cores and multi-threading to do more do more calculations in parallel. And so when we talk about the difference between the latency of CPUs versus GPUs, um, the real structure is embedded in how the design occurs. With the CPU design, you're going to have different, arithmetic logic units that are going to be the primary focus on that chip, as well as control components and a larger cache and DRAM to make use of. And so, that the various ALUs can be used for reducing the operational latency. And then we have larger cores that we can use for doing converting uh, or reducing off memory access to cycles, so you can easily access data that is on the core or on the chip quickly. And then you have different branch mechanisms that are also utilized to help reduce some of the computational latency that occurs, and a lot of um, the cache helps with the data latency from moving data from the ALU back to the cache as needed. Some components here. Now, GPUs are constructed a lot differently in that you have multiple cores that you're able to make use of. So, and each core has a much smaller cache and compared to the CPU design. So if you look at back at the CPU design that we just did, where you had your control and a small cache with DRAM, here we have integrated that, but much smaller depending on the GPU cores that you're making use of. And so with that, we're going to have the caches are going to be a lot smaller, and that helps to boost memory throughput for quick computation. You'll have simpler controls and reduced branching. So it reduces a lot of the complexity, like for branch predictions for different um, chip operations that you needed. And it also provides for more energy efficient cores that you're able to make use of. And so that's basically there to try to reduce some of the throughput needed on the pipeline. But what this means is that GPUs are most beneficial when you have a number of different operations that can occur in parallel and that do not require a lot of memory for each of those operations. So GPUs allow for us to take more advantage of being able to thread and parallelize our logic. So that helps to reduce um, thread latency, essentially. So an important thing, and this kind of just sets the premise, is that, the heterogeneity here in computing, the most efficient applications are going to be able to make use of all of those different components, even CPUs and GPUs, to make sure that, sequential parts are executing efficiently, when they're bound with when latency is important. But then when you have high throughput computations, you're making use of the GPUs as well. And, in the future, there'll be quantum processing unit components as well, more commonly available, and larger systems already do integrate that as well. So different factors and things to take into consideration as you try to understand ways to optimize and improve your applications. And so, parallel computing is definitely taking on more of a heterogeneous perspective now, with, of course, scientific simulations, engineering simulations, data analysis, which is always a part of, even now, more scientific simulations. A large part of it is data analysis. And then, such as financial analysis, medical pharmacological modeling, and other areas. So CUDA can be used and applied to various different domains. And so at this point, do we have any questions or comments or thoughts from anyone? If we could maybe get a show of hands, who is completely new to CUDA and you've never heard or done anything with CUDA before? If anyone could raise their hand. Cool. So we got a few people. And so hopefully, as you continue on your journey in scientific computing, it's definitely an area you'll want to explore and try to incorporate. Um, and so with that, we'll talk a little bit about the importance of scalability and portability. And again, this is just a lot of this is kind of setting the mindset and the background before we get into more advanced using CUDA in more advanced ways. So what we want to make sure we keep in mind is that, a lot of the advances that we've been seeing lately in computing have been largely driven by hardware up until about the 5 or 6 years ago, where we kind of reached a limit, and then there were more software-based approaches to try to improve productivity. So with that, it's important to consider that software plays a large part and can dominate the system costs. And so, you know, when you consider the components or the architecture of a chip and you break it into what, like, different lines per chip, um, if you have more efficient software lines, then you're going to have a more cost efficient system. While hardware, it increases over time, but not at the same rate as software, because hard software changes occur. Um, you know, Imagine every time you have a software update. So making improvements in software, it has a bigger impact. And so what we want as we advance is for future systems to be able to try and minimize that software redevelopment costs because it occurs very rapidly. And so one way that we consider, breaking software costs or limiting that software costs is making sure that we're creating applications and software that are scalable. And so when we mean scalable, it means that, as you run the application on more cores, that it does not have the performance does not decrease. It runs efficiently across those cores. And even as you update to a new architecture, you want it to run efficiently on those newer cores that maybe have newer hardware logic as well. And so with scalability, we want to consider is, okay, so we have an application and does it run efficiently across various cores? And so those same application cores, you want to run that application efficiently across each core. So when we think about scalability when it comes to hardware and performance costs, one way that we kind of have been able to do that is by increasing the number of compute units that we have, as well as the number of threads and increasing the vector length. So that adds larger computations that we can do, as well as the pipeline, the number of instructions that we are able to store without having to go to memory, as well as our DRAM burst size and other components that we use to try to minimize latency and you know uh, memory limitations as well. So what we're going to be focusing on is understanding scalability and portability, how those applications can run on different cores, and figuring out how to integrate those heterogeneous components as well. So if you have an application running on different cores, making sure that it can make use of those cores efficiently. And so that means having a programming paradigm that is portable. It's not just for executing on a CPU or GPU or a quantum unit, that it can efficiently run across those different cores um, using different interfaces as well as, however the architecture might be constructed. And so when we make considerations about portability, what we want to make sure that we consider is the different instruction sets that we're going to be used. Is this going to be like the ISA, is it a x86 base or is it, ARM based? Also understanding the different limitations for CPUs versus GPUs. What type of parallel models are you going to be using as well? Threading, SIMD, or very large integration. So it can vary, as well as shared memory versus distributed memory. So those are all kind of different factors that can affect the portability and performance of applications across different systems. Okay. And so we've talked a little bit about the importance of scalability and portability for um, improving applications. Before we get into our introduction to CUDA, we'll want to just do a little overview again of our system here, current system here at Nurse, and how it is constructed. And so again, we name our systems numerically in, you know, one to so forth. Currently, we're on Nurse 9, which was named after Saul Perlmutter. And In June, we announced our next generation system, N10, which will be Doudna, named after Jennifer Doudna, who is a research scientist at Berkeley Lab who um, received the Nobel Prize in Science for advances in CRISPR technology and gene editing. So each of our systems we design based off of the needs of the Department of Energy, and our goal is always on increasing energy efficiency as we advance those architectures as well. And so again, as I mentioned, Nurse 10 is named after Jennifer Doudna. Our current system, Perlmutter, is named after Saul Perlmutter, who was awarded the Nobel Prize in Physics for accelerating the expansion of for determining the rate at which the universe was expanding. So he is a research scientist here at Berkeley Lab. And one request that he had was that he wanted users to be able to log into the system using his first name. So he has a login node named after him called Saul that users can log into. And so let's talk a little bit about the architecture of Perlmutter. We talked about some of the importance of how we construct different nodes and node types um, and different chips and GPUs versus CPUs. So on Perlmutter, we have two node types. We have the CPU nodes, and then we also have GPU nodes, and the GPU nodes have GPUs incorporated and only one CPU for that memory as well. But with the CPU, you have more CPU cores that you can make use of. And so one thing that you want to keep in mind is that are combined into different blades. And so, each blade can have two GPU nodes or four CPU nodes. And then what we also want to consider is that those are then stacked into racks. So each blade, they're stacked sideways, and those become our server racks that you essentially are able to access. And so if you have not been on or toured the machine room, you're able to see the compute racks that we make use of easily as well. About that. Is everyone able to still see my screen fine? Had a couple of pop-ups pop in the way. Okay, good. All
All
right.
good. Yep.
All right. And so our compute racks each will have 64 blades within them. So you can see kind of how not only are our systems very they're not homogeneous. There's a lot of heterogeneity within them, and they're also very hierarchical in the way that they're configured to make use of. So it's different kind of hardware layers that you have to consider when you're developing your applications too. And this is what, if you go on a machine tour, what they actually look like. Okay. So now we've talked a lot about portability and parallelization. So now what we'll do is we'll get started with CUDA C. But first, what I want to do is I'm going to take just about a 2 or 3 minute little break just for my voice. Um, so maybe let's take a little 5 minute break. If you need to do a little bio break or something, we'll do that. And then we'll jump into the second part of this training, introducing CUDA C and the CUDA Unified Data Model, as well as just go through some of our examples in the Git repository too. So let's take about 5 minutes, and we can start back at about 11:47.
Just so you know, there is one question in the Q&A doc
Okay.
about how CUDA runs on Grace Hopper chips, and like, is it any different? Um, my initial thought is that the main difference between the GPUs we have available now and the Grace Hopper chip is that there's a CPU and a GPU right next to each other and they can share memory. But since NVIDIA CUDA is their proprietary language and these Grace Hopper chips are NVIDIA chips, I'm sure CUDA will run the same
Yeah,
on those chips since it's written to operate those chips.
yeah, and basically it just basically depends on how they you know, the module for like what we load for NVIDIA on Perlmutter is pretty much the same. You know, it's under the hood, no different.
Yeah.
Good question, though. All right. So we'll get started back in about 3 minutes. All right, everyone, we'll go ahead and get back started. And so now we will segue into understanding or introducing CUDA C. And first, what we'll do is we're going to focus on, again, just understanding where CUDA fits into in the large scheme of things within NVIDIA's strategy for portability and computability. And so, one way or a number of ways in which NVIDIA tries to accelerate application development is by focusing heavily on having an ecosystem that focuses on different libraries, compiler directives, as well as various programming languages. And those all work um, in concert to help accelerate application development and accelerate the computation of applications. And so one way to do that is by making sure that the systems and your hardware have libraries that are easy to use and easy to make use of. So we have libraries that can be used to enable GPU acceleration um, without, having a large understanding. So you don't have to be Einstein to just use the libraries. Make them very easy to use that can be drop in, flowing, following standard APIs so you can easily switch them in and out, and making sure that the libraries offer high quality and efficient implementations of the functions that may be needed and ensuring that they apply to a broad range of different application types as well. And so NVIDIA has a number of different scientific libraries that they use that you can make use of for accelerating your scientific development. So you have, for deep learning, different libraries to make use of from DeepStream, TensorR, and, other libraries. They have linear algebra libraries, cuBLAS, cuSparse, cuSolver, and as well as signal, video, and image. And then you also then have different parallel algorithm libraries that you can make use of, like Thrust as well. So one approach for NVIDIA to accelerate that type of scientific development is through having various libraries to make use of. And so one way about that is using thrusts. So this is just kind of an overview of different ways that you can program and parallelize. And thrust allows for you to access and define the host and the device that you're going to make use of. So this just gives you a simple example of how you're able to do a vector addition. We're going to go through a similar example for CUDA a little bit later as well. And so another way that you want to also do that is making sure that you have things that are easily able to compile. And so the compiler directives, you want those to be easy to use and of course portable. So with the ease of use, the approach is making sure that those compilers just take care of any parallelism and parallel data management that is needed, ensuring that, it's portable. So if you have to constantly change the compiler directives based off of the hardware, then it's not going to be portable and easily deployed, and ensure that that the performance can vary with different compiler versions, or it that it can execute across different compiler versions efficiently. And so one way to do that is using OpenACC directives as well, and those provide different compiler directives that you can have for C, C++, and Fortran. Very similar again to if you've used OpenMP as well. So similar approach for doing the same computation as well. And now another way, again, to do that is making sure that you are exploiting programming languages with languages that are able to give you the most performance and also offer the flexibility to have those applications accelerate appropriate. So when you think about performance with the programming languages, you want the programmer to be able to have control of the parallelism and the data movement that is going to be needed within the application. You want it to be flexible, so you won't want the computation to be limited to a certain set of library patterns or directives. And then you also want to be able to allow the programmer to express as much detail as is needed as well. So that's another way in which the NVIDIA ecosystem tries to accelerate applications is by allowing for programming languages to be uh, performative and flexible to help accelerate scientific and computing advancements. And so GPU programming in the NVIDIA ecosystem can take on a number of different forms with GPU programming languages that are available. In various ways, you have, different languages that you can use from numerical analytics. You have different Python programming languages available, Fortran, of course, and C, C++, and C Sharp as well. And so CUDA C and CUDA C++ are also used. You have PyCUDA that is available as well for programming on GPUs too, and, and Thrust as well. All right. And so one way that we can discuss how to make our applications um, portable and easy to use is by understanding CUDA C. And so CUDA C is basically just a wrapper kind of for the C programming language. That's really all it is to enable accelerated computing through the GPUs using C constructs. And so now we're just going to dive into some of the essential basics of some of the CUDA C API functions and understanding how exactly to use them on a CUDA host device and how you can access device memory and host device data transfers as well. And so one simple example to understand about the data parallelism is to just simply make use of the example of a vector addition. And so, with a vector addition, of course, you have however many vectors that you are looking to combine together. And so you will have vector A and whatever index from, 0 to n minus 1, and vector B from 0 to n minus 1. And you're going to add the results of each individual vector together. And then that result gets stored into vector C for each index. So this is just kind of a typical um, example of how a GPU would be beneficial when you have to do similar operations contiguously upon data points that can be quickly stored in a GPU core for quick access. And so, vector addition in a traditional C code, let's just do a little comparison, is that, you have your function header to do the vector addition, and you're passing in the pointers to, hardware element A, hardware element B, and hardware element C. And then you have integer n to denote the number or the index of it. And so you're executing that addition from, 0 to n minus 1. And for each vector, it gets added in, host device A or host device B and added to C. And so in memory, again, you just have that call to that vector add occurring. And so now let's kind of consider what is going to be happening in a heterogeneous type of environment for that vector addition. So we have our device having the host memory access and that CPU. And so part one is about making sure that you allocate memory for that device. So you'll allocate memory on the device memory for the GPU. And so you're allocating device memory for A, B, and C. And then you want to make sure you copy A and B to the device memory. So then within the kernel, you're performing the actual operation in part two, and that is where the operation gets stored into the new vector C. And then the device result gets sent right back to the host as the result from that. And so this is a pretty quick and easy and high level overview of how operations such as vector addition occurs. Is basically you are taking it from that host, the CPU, and transferring it to the device to do the different parallel operations. And then that result gets returned right back to the host memory as well. So taking that into account, um, how do we realize that and see how it is actually represented on a CUDA on a GPU? And so what you want to consider is that you have your host CPU that is going to be connected to the GPU device memory, and the block in which or how the memory hierarchy for GPUs or for CUDA for NVIDIA GPUs or is that you'll have your device code that can read the read-write registers per thread, and then you'll have read-write for shared memory, global memory as well. And then what the host code is able to do is transfer its data to and from the grid, the global memory for the device to be able to access. So we'll get into more in part two of the Bird's Eye CUDA series. We'll get into more detailed memory models within CUDA. But at a high level, this is how CUDA reconciles memory movement from host to the device. And so what you want to make sure that you're able to do considering if we want to take the traditional C example and create a CUDA version of it, it's going to take a little bit more memory management and memory control to explicitly denote um, what device is going to be used and from what host. And so what you want to do is remember in part one, we have to allocate memory. And how that is done is using the CUDA malloc function. And so that's just going to allocate an object on the global memory for the host and the device to be able to access. And so you'll pass in the parameters of the address of a pointer to that object, as well as the size of the allocated object in bytes. The other operation that is needed is once that um, operation is moved from global memory back to the host, then you want to deallocate that memory because we all have a limited amount of memory that we can make use of on a device. So you use CUDA free to free up that object memory or the object global memory. And again, that's just one pointer that you pass in, and that's just a pointer to the object that needs to be freed. And so another way in which you, or another function that's used in order to copy um, data from the host to memory to the host from host to the device is using the CUDA mem copy command or function. And that's going to be how, again, you can transfer your data from your host to global memory. And so all that's going to do is going to pass in you'll need to pass in the pointer to the destination, pointer to the source, the number of bytes copied in that type of direction as well. And so let's see how that would be in action with our updated example on vector addition. And so here we have our vector add command occurring, and then we have our function declaration for vector add, and we see we're passing in a pointer from host A, host B, host C into it. And then inside of the vector add, what we're doing is we're allocating memory for each device. So we allocate memory for our device A, for device B, and device C, and we pass in the size as well. And then we also want to copy from the memory from our device or from our host into the device. So we're going to do that copy and we're going to do a mem copy from host to device as well for A as well as B. And then we'll do the application, the operation. And then we want to copy the result again from our hosts to back to the device. And so this is going to give us our mem copy of the result. And then what we have is we are going to free up all of the memory that we originally allocated. And so that is basically giving us a quick and easy understanding of how we're able to do our vector addition and what is occurring as we copy from one host device, from one host to the from host memory to device memory as well. Okay. Do we have any questions about any of the API calls that we use for um, CUDA malloc and CUDA memcopy?
Yeah, I have a question.
Go for it.
So if our vector size gets very large, then do we have to balance like two sides? Like we need to copy this large vector from CPU to GPU, which will take some time of copying the data if the vector size is very large. Do we have to balance between the gain we will be getting from doing it on GPU with the amount of time it will take to copy this data?
Yeah, and that's another consideration is that making sure if your data can't be broken or you forced into a block that will fit on the GPU, then it might not be best for you to use that version or to figure out, or maybe for that specific kernel in your application, maybe that's not optimal to use GPUs for it. So that's again another consideration with the reduced memory that's available for you to access on a GPU core.
I see. Okay, thank
Does
you.
does that make sense?
Yes, yes.
Okay. And
Okay.
Sean, you had a question?
Yeah, so if I understand this correctly, so within our function we allocate D, A, B, C, and that's within the host. And then so malloc, so does with like these red lines, does that allocate the memory on the device? And then with the green, the memcop, that actually is putting the data onto the device? So with those two steps like broken up?
Yep, exactly. So right here, so just like it's in red here, that's allocating the memory that we're going to have on it. And then we're
Okay.
copying it here.
Mm-hmm. And so the global memory, I guess I must have missed that. Where does the global memory actually exist? Is it on the device or on the host, or it's like a shared memory space?
Mhm. So for each, sorry, so here is the global memory on each of the nodes here. So the CPU here, and then you have your GPUs that are accessing it, and global memory is accessible by both.
Okay. So it exists on the node, not exactly on the GPU itself.
Yeah, so if we go back, Sorry. It's easier to explain it using, if you go back even for, so even like here, we have within our nodes, we have the global memory connected and both the CPU and GPU have access to it.
Ah, okay. I got you.
Hmm? Does that make
Cool.
sense?
Yeah, that does. Thank you.
Okay, cool. Good deal. Right. Any other questions? Can everyone see my screen fine again? All right. So again, yeah, that's the basic operation that we do have for CUDA malloc and mem copy, as well as once we copy it from our device back to the host, and then we want to free up that explicit memory allocation as well. And so one way that we also have that is being able to access the unified memory that is um, off the actual device. And so with that, we can also access it using CUDA malloc manage. And then you'll have a pointer to it, and then the size that you're going to be using as well. And so with a single memory space, we can have all of the CPUs and GPUs within a node being able to access. It allows for a single copy of the data to be maintained, and it can be used to manage the CUDA data movement for as well. And so it's compatible with CUDA malloc and CUDA free, and it can be optimized using other optimization approaches like CUDA mem advise and CUDA mem prefetch and other asynchronous directives that you can use. And in part two, we'll get into of the call, we'll get into more detailed advanced directives for understanding how to more explicitly manage memory in CUDA as well. And so at a high level, if we have, our unified memory and we have our different devices, we can use CUDA malloc manage here and passing in the pointer to um, each of those hosts that we are going to be collecting or managing, as well as the size of that. And then we can do our vector addition. And then again, what we're going to do is free that up later as well. And so another thing to also try to include is making sure that you have appropriate errors in place. If there are any type of errors in copying from host to device or device to host as well. And again, that's just, typical C constructs. Okay. And let me check time. Okay, good. So actually, at this time, what I would like for everyone to do, if maybe we can go ahead and make sure everyone is able to access the Git repo and make use of that appropriately. And then we'll just finish up with the last few couple of slides. So if you yeah. Mhm. 1 second. Logging into Jupyter really quickly. Enter my code, and I don't seem to have my phone with me. Just right. Apologies. So if everyone, you can either use Terminal if you would like, or you could use Jupyter. And so let's share this really quickly. So if you for the activities, you can just clone our GitHub repo here. And let's take a few, maybe like 2 minutes to make sure everyone's able to just go ahead and do that once you've logged into Perlmutter uh, or logged into Jupyter. And you can do it via terminal or however you prefer to complete everything. You can just copy the commands. We have it there, so. So if everyone just wants to take about, I'll give you about 3 minutes to complete that. And so within the files, we have three uh, pertinent examples, or four, one including the vector add example that you can make use of. Within for each script, you should be able to access um, the batch script for each one, for each example. So if you wanted to run the hello world one or the vector add one, all you have to do is just do your sbatch and then hello world.sh to submit, as well as just run make to compile all of the examples and using the reservation that we have available. So your script file should have everything there for you to make use of. You'll want to just make sure your account is TRN017. Use the shared queue and the reservation for today. These flags should already be set in the repo for you too. So these will just be a few of the simple examples for part one. And then part two will have more detailed examples for us to work through as well. Training counts expire August 31st. So it'll be after part two.
I have a question, excuse me.
Mhm.
So how can I specify how many GPUs I have to run or I want to run on?
Okay, so which constraint when you're how many GPUs or how many threads that you want to?
Uh, Actually, I want to know what the difference and maybe both. Like, how can I do both?
Okay, so with the GPU, you can specify with the you'll specify how many nodes, and then with the -G flag, if you see that in the SFATch file, that tells you how many GPUs you're going to allocate. So for this, within the hello world, it's just going to run different threads if that's the one you use. So we'll get into more details about the threading um, at the end of actually coming up next, and then for part two. So right now you can just focus on using one GPU with the -G flag, but you don't need to worry about threading actually for now.
Okay, so if I want to use more GPUs, I just change the G flag, but I don't have to do anything in my code itself.
For the time being, yes.
Okay, okay, thank you.
No problem. Any other questions?
There's a few in the Q&A doc if you want to take a look at those.
Okay. Let's see. Okay, so towards the end. So, Sean, could you clarify a little bit about your question?
Yeah, it was pretty much what I had asked
Oh,
live
okay. Oh, I'm
for the
sorry.
most part. I think
Okay.
I just worded it poorly in the document.
Okay, I got you. I got you. Let me put a quick um yeah, and we have another question from Alfred asking about the syntax for could you clarify what you mean, Alfred, about the difference between because with the CUDA mock, it's basically just kind of like a declared function versus um because you're denoting that you're doing a pointer to a device pointer. And so when you're writing to CUDA, you're writing to that the device memory address into the device memory pointer. So like the float that you use is for the size. So you'll denote void star and then that device that you're looking to pass into. And then you could also allocate it on the GPU memory as well. And so the the notion of the star D_A is basically denoting that that is the device memory pointer. And then you're passing in the value of, you're casting it as just a void. So no implicit type. And then you're passing in the size of that, if that makes sense. Easier for me to tell you that versus typing, but we'll definitely have a written response. And for everyone, if you have a question, the PDF will be posted on the event page with all responses and questions, removing any identifying information as well. So even after today's call, if you do have a question, please just come back to this Q&A document, and it will be addressed as well. Okay.
Hi. I'm getting an error that I have an invalid account or partition. Is it because my account is not added to the list or something?
Oh, did you join late?
Yeah, I joined like one or like 17 minutes later or something like that.
Or did you, I'm sorry, when did you register?
I think I registered like 3 weeks ago.
Okay, so your account should be on there. That might be the issue. I will ch After this call, I can check and then I can add you to it.
Gotcha. Thank
If
you.
you could please message me your username.
Okay, sounds good.
Okay. Any other questions? All right. Well, we will try and work through a little bit more here with the data parallelism. Okay, so now we're going to get a little bit more into breads. Let's see. We have about 5 minutes. So what we might have to do is just we'll pick off with threads on part two. That might be a good way for us to pick up, and then that'll give us into more advanced features as well as using multiple threading for multiple threads and multiple GPUs as well. So for the time being, if you could make sure that you're able to compile and run all of the example scripts that we do have, and if you're having a problem with the reservation, just please message me or email me your username so I can go ahead and add you to the training account. And the training accounts will expire August 31st. So you can feel free to toy around with that allocation. Um, do we have any other questions? And I'm going to respond to the ones in the Q&A doc. Okay, so one question I'm seeing someone typed is the best way to debug CUDA codes. And so in part two, we'll introduce NBProf and Insight, which are two ways in which you can debug. They're NVIDIA's suite. And then we also have, I believe that we are planning a training on that. Uh, Helen, did we have an Insight training planned?
But what?
An NVIDIA Insight training. Did we have one of those planned?
We had one as part of the NUG GPU programming in end of April
Okay.
in May.
So,
So it's recorded. You should be able to find the recording on our website.
okay. Okay. So, for the person that asked that in the chat, if you want to, we do have the recording from the Insight training that we had from our NWays GPU training in April. So you can look at that via the past training events link that I have in the slides. Okay. Well, if there are no other questions, we can end that in today at this point, and we'll pick off in part two. If you haven't registered for part two, please make sure you do. If you do not have a training account or you join and you did not submit your training account, please do so. Also, please complete the following survey for us today. If you could do that before you leave. and let us know your thoughts on this training series. And also if you have any recommendations for future training ideas and events as well. Alfred, you should register for part 2 as well. And you're more than welcome, Encore. Just 1 second. I'll get that for you, Alfred. Thank you for attending, Trevor. So this is the website for the event page for the part 2 of the call. So if you could, please make sure you go ahead and register. You're more than welcome, Alfred. Please, if you have not, please do complete the survey for us. Really, that is how we know what trainings are most useful and what needs to be worked on. So please give us as much of your feedback as you possibly can. You are more than welcome, Enwell. Thank you so much for attending.